Okay, let's start with homework assignment number 5, the second law of thermodynamics. Okay, problem number 1 is giving me that I have a cyclic machine. Shown on the figure, I can draw the figure. The figure tells me that I have a reservoir, a high temperature reservoir at TH, and of course I have a low temperature reservoir which is TL, and I tells me that I have a cyclic machine that works between those two reservoirs to give me work, and this of course QH, and that is QL, which is heat rejected. And then it gives me some numbers, like for example it tells me that TH, so TH is 1000 Kelvin, and it tells me that also TL is 400 Kelvin, and the work, yeah, and it also tells me that QH is 100, sorry, 325 kilojoule, and it tells me that QL is 125 kilojoule, and then it asks me if this is a reversible heat engine or irreversible or perpetual machine, which means that it's impossible. So the thing that I do is that first of all I need to find what is the Carnot cycle. So the Carnot cycle efficiency. We have learned that it's 1 minus TL divided by TH. Now, if you do so, then you get what is TL? Is now 1 minus 400 divided by 1000, and that's going to give you 60%, right? So for the Carnot cycle, the efficiency of Carnot cycle is 60%. Now I need to, what is the efficiency for the heat engine itself now? For the heat engine, it's the real one, because I have also data to check the real one. So the efficiency of, let's say, for real one, I don't know now, of course, if it's real or not, because it can be also equal to Carnot. If the efficiencies are equal here, it will be real and Carnot at the same time. But let's assume that this is what he claims, that it's real. And that's going to give you, it's again, it's the same, it's work divided by QH, because this is the definition of efficiency. And the work here, did I write? I didn't write the work here. I can write it here. The work is 200 kilojoule. So it's 200 divided by 325 QH. And this, if you do this, that's going to give you an efficiency of 0.615, which means that the efficiency is actually 61.5%. Now, if you compare between those two, you know now that it's the efficiency of the real one is larger than the efficiency of Carnot. And we know that cannot happen, because we know that according to what we have learned, according to Carnot, the best and the highest efficient heat engine that you can connect between those two reservoirs will have the efficiency of a Carnot. You cannot construct a real engine that hasn't or more efficient than Carnot efficiency. So this will be impossible, and I will write it by a different color so you know that this is important. It's impossible. So if somebody is telling you that I have done this machine, then you know that it's not correct. Okay, let's start with problem number 3. Now, problem number 3 is telling me that I have 1 kilogram of air as an ideal gas. It's very important um, that we are dealing with air as an ideal gas here. And here is the mass, which is 1 kilogram. Execute a Carnot power cycle. And this power cycle have an efficiency of 50%. So we can start writing at least what we have. The mass of the air is equal to 1 kilogram. And then it's of course a Carnot cycle. The system undergoes a Carnot cycle. And then it's also telling me that the efficiency of Carnot cycle, and remember this is an ideal efficiency and this is the maximum efficiency that a heat engine can or work in between two temperatures can reach, and that is 50% in this case. The heat transfer during the isothermal expansion is 50 kilogram, and you can see here the problem is expecting you actually to know the Carnot cycle for processes, and I think also if I start with drawing it here, I think things probably would be easier to explain. Now it's an ideal gas, it's air, and we know that PV diagram, I can take also different color. We take the PV diagram for air for a Carnot cycle. It looks something like this, that we have two isothermal and you have two adiabatic, which means that we start here 1, 2, 3, 4, and we go like this. It's a heat engine, and we explain that this one and this one are isothermal, and this one and this one are adiabatic. Now it can also be polytropic, for example. Um, so the problem is expecting that you know this, because then it starts to tell you at the end of or the heat transfer to the air during the isothermal expansion. Where's the isothermal expansion in this case? The isothermal expansion is process 1 to 2. So this is the isothermal expansion. So it's like telling me that Q in this case is 50 kilojoule. So I can write Q in, which is QH. So the heat transfer from the high temperature reservoir, that is 50 kilojoule. And then the pressure, now tell me at the end of the isothermal expansion, so here, process 2, this is the end of isothermal expansion. At the end of isothermal expansion, the pressure is, so P2, I can write here, is equal to 574 kilopascal. And V2 is 0.3 meter cube. That's all the information that I have. And then it asks me to find the maximum and minimum temperatures. So I need to find TH here and TL here. The pressure at the volume at the beginning. So it needs to have P1, T1. It can ask me about also finding P2, V2. Or it can ask me something about 0.4 here, for example. So you have some information, and by you understand the Carnot cycle, you need actually, or you can using the ideal gas law, you can find all the volumes, all the temperatures, and all the pressures at the four corners here for states or processes, and you can calculate the work. The work and the heat transfer for each four processes is also um, has to be determined, and also sketch the cycle in PV. We already have it on PV here. Um, so it's as you can see, you have some information, and then your understanding of Carnot cycle, together with information that you know, should lead you to sort of solve A, B, C, D. So let's start with this. I can also draw it here, and just for records, you see I'm drawing Carnot cycle many times because I want just almost to print it in your mind. So this is two isothermal, and then I have two adiabatic. So this is 1, 2, 3, 4. Now, of course, for the assumptions, if the assumptions that we have is that it's a closed system, we also assume the air as an ideal gas. And we also assume that the change of volume is the only form of work. And that means that the boundary work is the only work that we have. And let's start analysis. We have some information about two mainly. And we have also Q in, remember. And then ask me to find almost the rest. We know the efficiency is 50%, so that's going to help us also in calculating some of the unknowns. And let's start with process 1 to 2, for example. What can we find there? Then process 1 to 2, we can find T2. T2 is not a given, but remember, always it's an ideal gas, so we use an ideal gas law, and if I write it down, B1 V1 equal to M R T1, but I can also write it to P2 V2, that is also M R T2. Now, depends on the type of information that you have. That of course helps you to calculate the unknowns. Look here, we have this is constant, and this is we have given. This one is given, and this one is given in the problem, which means that I can find T2. So T2 can be calculated as P2 V2 divided by MR. And remember, P2 is 574 divided by Pascal. And then you have V2 is 0.3 meter cube, that's given. And R for the air is 0.287 kilojoule kilogram Kelvin. And the mass, I can also write it here. The mass is 1 kilogram. So you actually know much. If you put this here, substitute them, you will find that T2 is 600 Kelvin. Now, remember that this line from 1 to 2, the process from 1 to 2 is an isothermal process, which means that T along this line is constant. And that telling me that T1 equal to T2 equal to 600 Kelvin. It's good to know this. Now, we know, I'll come back to this, but we know also, because one thing which is also given in the problem is it tells me that the efficiency of Carnot of the cycle is 50%. Now this, we know what is the efficiency of the Carnot as a function of temperature. It's actually 1 minus TL, or T cold, divided by TH, temperature of the hot reservoir. And this temperature is already known because we calculated it as 600. This is T1 or T2. And this is given, so I can find TL is equal to TH multiplied by 1 minus the efficiency. It's just a little bit of mathematics. Now, TL is equal to 600 multiplied by 1 minus half, and that 300 Kelvin. This is equal to T3 and equal to T4. I can also draw it here, the cycle again, and tell you that the cycle, Carnot cycle, 2 isothermal and 2, this is 1, 2, 3, 4. And I can say, no, I can say that this here is TH equal T1 equal T2, and here this is a constant TL equal T3 equal T4. Okay, now this is one of the things he asked about, and now we can start with finding the work and the heat for the processes, and we start with process. I can write here process 1 to 2. What can we do here? Now, the first law of thermodynamics, as we did in the previous problem, the first law of thermodynamics is telling me that mass multiplied by the difference in internal energy is equal to the heat transfer minus work for a process. And for an ideal gas, that's also a very important fact, is that for an ideal gas, and I will write it down here, NRED. For an ideal gas, we said that internal energy is a function of temperature. So the internal energy of an ideal gas is actually a function of temperature of the gas, which means that if this temperature is constant, that tells me that so if the temperature is constant, then U is also constant, which means that from U1 is equal to U2, which also means that delta U, the change in internal energy, is equal to 0, and that reduced the first law of thermodynamics. This will be 0, and the first law of thermodynamics will be reduced to that the heat added is actually equal to the work done by the system if we are talking about an isothermal expansion from 1 to 2. And this tells me that the work, I can start from, because we said Q in here, that was 50, right? Or 50 kilojoule. So if we said what is the work, how can we calculate the work in terms of or boundary work? If you remember, boundary work was 1 to 2 PdV, and that for an ideal gas, remember, PV RT, which means that the pressure is mRT divided by V. This is constant because temperature is constant in this case, R is constant, and the mass is constant. So put this into the integration. If you put P into the integration, we have done this many times before, I do it here very fast. That's mRT divided by V dV. And then you can take mRT out and just integrate from dV divided by V, and we know that this one is equal to mRT, and that is nature algorithm of V2 divided by V1. So for an isothermal process, this is how we find the boundary work, or how we calculate the boundary work. And if we go back, if so I can see work from 1 to 2 is equal to RTH length V2 divided by V1, and that is equal to Q from 1 to 2 because delta U is 0 in this case, and that is equal to 50 kilojoule. Now, what do I know? This is given, this is constant, this is already calculated. V2 is given, V1 I don't have, this is given, and of course the work is given, which means that I can calculate V1. And remember again, I do that, where are we now? 1, 2, 3, 4. So I'm trying to find V1. This is PV diagram. And to do so, I can immediately say then V2 divided by V1, this is equal to the work from 1 to 2 divided by mRTH, and that is 50 kilojoule divided 1 kilogram multiplied by 0.287. This is the air constant, or the gas constant for air, multiplied by TH, the temperature, and that's going to give you 2904. So length V2 divided by V1, that is 0.2904, which gives you that V1 is actually 0.224 meter cube. And that's you ask in the problem to calculate. But we know also that T1 equal to T2 equal to 600 Kelvin, right? And which means that T is constant, and mRT equal PV, that's we know. So if this is constant, it means the whole thing here is constant from 1 to 2, which means that I can actually write P1 V1, do like this, equal to P2 V2. Now this is already calculated, it's here. This one and this one I have. I can find P1. This is where you ask, or the maximum. Remember, or you can notice that P1 is the maximum pressure in the cycle, or in the Carnot cycle. So I can write P1 is equal to P2 V2 divided by P1, sorry, divided by V1. I have this and that one, and if I do so, so this is, I can write down the whole thing. It's probably better to write it also in numbers, that you can check it for your answer. And that gives me, what is P2 is given in the problem as 574.4 kilopascal multiplied by 0.3 divided by 0.224, and that gives me 769 kilopascal. So that is P1. So now I have T1, P1, T2, P2, V2, and I have V1. So point 1 and 2 are fully defined. So let's start with the, and process 1 we also calculated the work, which is equal to Q, and Q is given in the problem as 50 kilojoule. Now for process 2 to 3, one, two, three, four, and now we are process 2 to 3. So this is it's adiabatic. So process 2 to 3. Now it's a adiabatic process, which means that heat transfer from 2 to 3 is 0. And applying the first law of thermodynamics is Q2 to 3 minus work 2 to 3 equal to m U3 minus U1, difference in the internal energy. And this is 0, and we can also use, now this is, I need to find, I can find this because I know the temperature now, and I can actually find this from the air table from A17, which is properties of air as an ideal gas, and I can show you here. I think I have it somewhere. Okay, so this is ideal gas properties of air, and in this table the air properties are given as a function of temperature. So if you know the temperature, you can just go and read here the enthalpy, and here is the internal energy, and this is probably you don't need to deal with, because this is actually not the entropy. Um, but for now, we consider we're dealing with, or we need to find the internal energy. So at 300, this is the internal energy how it reads, and at 600, because this is the true temperature that we have, this is the internal energy we read. So if we do so, we can calculate the work of from 2 to 3. So I can write those values, so can you track them? And I can say that now U3 at temperature equal to 300 Kelvin, that reads as 214.07 kilojoule, and U2 at T equals 600 Kelvin, that's read as 43478. And now I can calculate the work as 1 kilogram multiplied by 43478, which this is U2, minus 21407, and this is U3. Of course, this work is an expansion adiabatic, so you can see here it's expanding, so it's positive work, and it has to give you positive work. If you know this, it doesn't matter which one you have, if U2 or U3, but you can see that this is 220.7 kilojoule, and that is the work from 2 to 3. Now, if you take the process 3 to 4 now, due to the different color, so from 3 to 4, and from 3 to 4, it's an isothermal compression. So, and if we have Q in here, we have Q out, or QL. Well, this is the same as, say, QH, right? And we know that it looks like, or it's the same philosophy in solving it as 1 to 2, as process 1 to 2. 3 to 4 is the same. One is isothermal compression, and one is isothermal expansion, and one is isothermal compression. So the work from 3 to 4 is equal to Q from 3 to 4. Why is that? Because delta U now we know equal to 0 in isothermal process. And I know also that from the absolute thermodynamics scale, we know that Q 3 to 4 divided by TL, so this is, don't forget that this is QL divided by TL equal to QH divided by TH, and QH is Q from 1 to 2, so this is Q in. Now, what do I have? I have this, and I have this calculated, and I can find this one. So I can write here Q 3 to 4 is actually 300 divided by 600 multiplied by 50 kilojoule, and that's going to give you minus 25. Now, why do I write minus 25 kilojoule? Although I don't see minus here, it's just my understanding is that it's a heat that actually rejected by the system, so it goes out of the system. This is why it's minus. And then the work from 3 to 4, which is equal to Q from 3 to 4, is also minus 25 kilojoule. It's also, again, we are compressing, so we are doing work on the system. This is why you have minus here. So it's and then I can also give this, because I'm not need to copy this and do this. And I can say that I need to copy this. Okay, so now we come to process 4 to 1. And process 4 to 1, so process 4 to 1 is similar to process 2 to 3, because this is an adiabatic compression. And when we say adiabatic, of course we know that Q 4 to 1 equal to 0, there's no heat transfer, and then we are left with the work equal to U4 minus U1. And from an ideal gas perspective, we know that U1 equal to U2 and U4 equal to U3, because there is no change of internal energy along an isotherm line. And so work to 1 is equal to 1 kilogram multiplied by 434 minus U1 4 kilojoule, and that's going to give you exactly the same amount of work as process 2 to 3. But notice that this is minus because it's a compression adiabatic. Now you can make sort of a table now, just so it helps you to also check for all the processes. And if you do this, you can just take like this, and you can write process, and this is Q, and this is work. And by doing so, you can, so process 1 to 2, Q we have calculated, or it's given actually 50, and we have calculated the work is 50, is expansion. From 2 to 3, there is no Q, it's adiabatic, and the work is actually the mass multiplied by the change of internal energy. We find it was 220.7. And then you have from 3 to 4, it's again, this is 25. It's an isothermal compression and no change in internal energy. So Q is equal to work, that's minus 25. And then from 4 to 1, then you have, this is 0, Q, it's an adiabatic, and this is minus 22.7. This is the work. And what we do is that we can, for the whole cycle now, if you take the summation here and the summation here, they should be equal, because we said Q for the cycle or equal to work for a cycle, right? And if you take the summation here, you'll find that this is positive 25, and if you take the summation here, you will find that it's also 25. And I can immediately from here, I can also find the efficiency, because he also wants us to find the efficiency. And the efficiency the efficiency, it's given in the problem, but it's good also to look here. And so the efficiency is actually the work of a cycle divided by Q in, and the work of the cycle, as you can see, is 25 divided by Q in, Q added, and that gives you 50%. And it just might take time to do this, but as you see, it's very consequent, and it's very very logical. So thank you.